Hello and welcome everyone. My name is Robert Smith, and today we are going to be discussing how to optimize your designs using simulation. During this presentation, we will be highlighting how Autodesk simulation can not only help ensure that your design works as expected, but is doing so in the most cost-effective and efficient fashion. Let's cover some basics. What is simulation? Simulation is an integral part of the digital prototyping process. Essentially, the 3D CAD model of your product is your digital prototype, the sole source of truth from which information flows to design and engineering, test and validation, manufacturing and production, and sales and marketing. Simulation takes place in the test and validation phase of the digital prototyping process. This is the phase of your process where critical questions need to get answered. Questions like, will my part break? How light can I make it? What happens when the temperature changes? These questions have traditionally been answered by building a physical prototype for testing, a costly and time-consuming process. Leveraging your digital prototype and the Autodesk simulation software portfolio, products can be tested in a virtual environment, thereby reducing or eliminating costly physical prototype iterations. Why simulate? Simulation leads to better products in less time and at lower costs. Performance can be predicted, and materials and design features can be optimized. This leads to a higher quality product. Costs can be reduced as fewer physical prototypes are needed for testing, and defects that may lead to unsatisfied customers can be uncovered while corrective action is still relatively inexpensive. Finally, innovation is fostered. Designers and engineers are free to explore more what-if scenarios, as testing these ideas digitally is more feasible than manufacturing a prototype. One of those crazy ideas may be your next big innovation. So when is the best time to simulate and optimize your design? Over the product development lifecycle, the ability to affect the functional capabilities of the design declines as the cost of making changes increases. The best time to identify failure modes is during the design and engineering phase. This way, the design is still flexible enough to make the necessary changes, and cost of those changes is minimalized. What makes Autodesk simulation different? Who uses Autodesk simulation? Autodesk simulation is built from the ground up to be fast and easy to use. Note the triangle graphic on screen. This triangle represents the entire community of engineers and designers. Traditionally, highly educated and highly specialized individuals, represented by the top portion of the triangle, have been relied upon to perform FEA analysis. These individuals are typically career analysts. They are expensive people who use expensive tools. This type of analysis is often done at the end of a design cycle for validation purposes. Autodesk simulation is part of a newer approach to simulation called upfront simulation. It's for the everyday engineer or designer. These individuals often wear many hats, and running analysis software may only be a part-time role. They need results early in the design process to help them make more informed decisions while the product is still in development. For this reason, they need the tool to be easy to learn and easy to use. Autodesk simulation serves these users. Autodesk offers a complete portfolio of simulation products to help you predict product performance by optimizing and validating your designs. The Autodesk simulation family of products enable you to integrate mechanical, structural, fluid flow, thermal, composite, and plastic injection molding simulation tools into your product development process, helping to reduce costs and speed time to market. What is Nastran? Nastran is a general-purpose FEA, or finite element analysis, solver. In the 1960s, NASA developed Nastran in an effort to standardize FEA solver codes, which were then in their infancy. The result was the code that NASA used to bring the U.S. to the leading edge of the space age. NASA released this code into the public domain, where it has since evolved and is now the basis of some of the industry's finest and most respected FEA software platforms, including Autodesk Nastran. Autodesk Nastran is proven and credible, providing accurate results for advanced linear, nonlinear, dynamics, and heat transfer analyses. It is scalable in that it is compatible with a large number of specialized third-party pre- and post-processors. What is Nastran In-CAD? Autodesk Nastran In-CAD is the power of the Nastran solver embedded in your CAD system. Available for multiple CAD platforms as a networked license, the CAD environment that designers and engineers are already familiar with then becomes the pre-processor for setting up simulations and the post-processor for reviewing results. This eliminates the need for a standalone simulation software package. Autodesk Nastran In-CAD supports a wide array of analysis types. Linear static stress and normal modes are commonly found in embedded simulation systems. Nastran In-CAD takes it to the next level with advanced nonlinear, static and transient stress, dynamic response, and thermal analysis types. Design optimization can be summarized as anything that helps reduce the costs or improve the performance of your design. Reducing weight, improving manufacturability, and increasing the quality of components all contribute to lowering costs and overall performance gains. There are a number of reasons why manufacturers don't optimize their designs today. Failure to optimize a design simply because it works in its current form can lead to parts being too heavy and much more costly due to increased material use. There may be concern that optimization will complicate the design and manufacturing process. Although it may initially increase upfront design cycles, the amount of material saved and the reduced number of parts in the design can be a huge cost and time saver further down the road. If we break product design down into two areas, cost and performance, an optimized design will be the ideal balance between these two areas. There are many factors to consider when looking to reduce the cost of your design. One of the first that you'll encounter is the cost of raw materials. Being able to simulate various materials to determine, for example, a part's ideal thickness can result in huge savings. Reducing a part's weight can have many positive downstream effects. Supporting components can be smaller, driving motors can be smaller, fasteners can be fewer and smaller, and even the costs of shipment can be reduced. Reduced component weight can also improve the life of the system. Less wear and tear on bushings, bearings, springs, and seals can increase the cycles to failure of a system. Less wear on replacement parts means less downtime for the end user. Customers today are more conscious than ever of the impact products have on the environment. What a part is made of, how much waste it produces, and how much energy is consumed in its life cycle are all factors in a consumer's purchasing decisions. Once you decide that it's time to optimize, factors like the various operating loads and the vast amount of materials to choose from have to be considered for new designs. Designs are often very complex, and changing one part can affect many others in the system. Any optimized components must be analyzed to avoid machine failure, and the new component's ability to endure the life of the product must be studied. Simulation can help. So how does simulation help companies optimize? Optimization is an iterative process. Testing iterations physically can be prohibitively expensive. Simulation gives you the digital test environment you need to validate your light-weighted components quickly enough to make the process economical. We will be looking at 3 demonstrations of ways to optimize with simulation using Nastran In-CAD. In the first, we'll see how the new shape generator tool in Autodesk Inventor will help us to remove unnecessary material. Autodesk Nastran is utilized to verify the strength and life cycle of a new component. In the second, we will look how quickly the design changes can be tested when utilizing plate and beam elements available in Nastran In-CAD. The final demonstration shows how you can reduce the number of fasteners in a design, utilizing the power of a parametric modeling system combined with embedded Nastran solvers.
Welcome to this technology demonstration featuring Autodesk Manufacturing Technology at Work. In this example, the design team has been challenged to increase throughput of this robotic welding station. Not only will their customer benefit from being able to produce more, the manufacturer could increase market share by offering better performing products and lower overall material and production costs through reduction of material used in the design. One significant difference you will see during this demonstration is the idea of predictive versus iterative design. Autodesk's shape generator technology enables engineers to define form based on the function that a component will perform. Let's have a look. One of the new Inventor Professional tools available is something truly revolutionary. It's called Shape Generator. This approach to design moves powerful analytic tools to the front of the design process, as opposed to traditional methods after the initial design concepts are created. This workflow enables users to drive initial design intelligently as a function of the physical constraints and loads the design is exposed to, as well as density, elastic modulus, and other properties of the material being used. Once the initial shape is defined, environment variables such as fixed, grounded, pin joints, or frictionless sliding constraints are added. Subsequently, loads such as forces, pressures, moments, or bearing loads can be applied. Preserved regions may exclude zones where material will not be removed. In this example, these are areas where the pivot joint, hydraulic cylinder, and clamp are mounted. Finally, a mass removal target is defined and the shape generator solver begins. This new technique promises to transform design productivity in ways not previously possible, as the initial model shape is defined primarily by the demands of the physical environment the part will operate in. This generative shape is then merged with the initial model volume, and then any one of a number of modeling techniques can be used to remove material from the volume, leaving the minimum amount of material required to match the results defined by Shape Generator. In this case, traditional sketched volumes are created and used to remove a bulk of the material that is not needed. Direct modeling and freeform tools may also be used, depending on the complexity of the part, and the shape of the areas that need to be removed. Fillets are added for blending purposes, and finally the part is saved, and checked into the vault with the rest of the new clamp assembly. The Shape Generator process was also used on the main clamp backplate, and here we used Inventor's Replace Component functionality to swap the new for the old. Finally, these changes are driven down to the assembly, and all existing instances are updated with the new configuration. With the new clamp design, it's time to make sure that it will last for the life of the ASCA welding fixture. We can do this right in the CAD design environment. We can even use boundary conditions from the Shape Generator study to save time and ensure consistency. In the browser, there is the bearing load from the actuator, as well as the two constraints simulating the pin and contact with the automotive component. The material also comes over automatically and can be used for the virtual test. We could run a linear static study and simply test for stress and displacement, but that's not going to be enough. We need to know if the clamp can withstand 300,000 load cycles. This requires fatigue calculations. There are numerous ways to constrain and specify the boundary conditions. In this model, we have a hole that can only rotate along its axis. We know that there is a fastener connecting the part to the hinge plate. With the use of rigid connectors, we can then have full control over the geometry. Turn on and off the ability to move or rotate in any of the 6 degrees of freedom to simulate a pin or spherical constraint. Let's also make a change to the load. Fatigue results are based on the behavior of the actuator force on the clamp. Is it loaded and unloaded? Does the load reverse in the other direction? The actuator in this case only applies the load in one direction. These load curves are fully customizable for any load condition. Finally, let's mesh the part or break it up into smaller pieces to be analyzed, and run the study, which only takes a few seconds to calculate on this component. Taking a look at stress, we can see the value is very low. Shape Generator did a great job of finding the best possible geometry for a lightweight component. We can also see the fatigue results show there is zero damage over the life of the part. Is it possible we can make it even lighter? Why not try different material types, even plastic? Nonlinear studies are extremely powerful. They provide high-fidelity results for all material types, including plastics, rubber, foam, and more. Let's edit the material we used in the previous fatigue study and change it to UHMW. We will find out how much of the load it will handle before it yields or maybe even buckles. Nonlinear studies are highly accurate. We will spread the load out in 30 increments and observe the results as it is gradually applied. We will also increase the load to ensure our safety factor is at least 2. Unlike linear static studies, we can watch the behavior of the part as the load is applied. Watch as the stiffness of the model changes and may even cause the part to buckle. This is something you will also never find in linear static results. They will only tell you if the material is going to pass or yield. Find out more about your design with fatigue, nonlinear, vibration, and thermal heat transfer. All within the CAD design environment. Even check the displacement of the model while the analysis is running. We can see that the part does in fact buckle at 1600 newtons. This does not satisfy our requirement of 2 times the normal load condition. Animations of the results may help to understand the weak points in the design for changes that need to be made in the model. We know that the design becomes unstable at 1600 newtons. By watching the animations, we can make better informed decisions for improvements to the stiffness of the geometry. Based on these results, we can confidently move forward with the model using mild steel. Using these types of studies, we can fully understand our design and run several what-if scenarios with various materials. Now let's check the design in with a message for the rest of the engineering team. From here, the engineering change order can be approved and released to manufacturing. Autodesk provides the technology for simulation-driven modeling using Shape Generator. Also validate parts and assemblies at any point right in the context of the CAD design environment using robust solvers for various types of studies, and manage it all in a secure and collaborative environment. Welcome to this demonstration on analyzing the weld frame in the ASCA welding fixture. We will be testing the structure for performance, simulating the load coming from the robot arm. The concern is whether or not the frame will provide adequate support. We also want to ensure there is not too much movement or vibration as the weld is applied to the automotive components in the fixture below. Let's begin. There are multiple approaches to set up the study which will provide various types of results to gain the information we are looking for. Are we concerned with stress, displacement, axial forces, bending? All of these questions will be answered in a matter of minutes. Solid elements is a traditional approach to meshing the model. However, here we will use shell and beam elements to gain results faster and even provide information that solids are incapable of. As you can see, the mid-surfaces are detected and the thickness of each part is automatically applied. Let's go ahead and create the mesh. Each of the components are shown with different colors and can be changed, making it easier to distinguish between them. Next, we will add boundary conditions to describe the behavior of the environment. It is held down to the floor at the bottom, and there is also a load that is applied from the robot assembly. In this first study, we will assume the robot is not moving. Stay tuned for dynamic loading conditions in just a minute. Contact conditions can also be created for all the components. Here we are ensuring there is a welded bond in cases where there is a possible gap between mid-surfaces. The solver runs very quickly for shell elements as there are fewer nodes to calculate compared to solid elements. This just takes a few seconds. There are several result plots available for shell elements such as principal stresses, maximum shear, and bending to name a few. And they offer an option to see the stress on the inside or outside of the tube without having to section the model or hide components. Now let's have a look at beam elements. The physical properties of each component contain several predefined options for the shape and cross-sectional size. Here we have a square tube at 100 mm with a 5 mm wall thickness. Once again, we will hold down the bottom of the weld frame where it is fastened to the floor and apply the same static load you saw in the previous study. The process for meshing and solving the beam elements is almost instantaneous. This allows us to run several what-if scenarios in a short amount of time. Now we have other types of plots available, such as axial forces on each of the steel tubes. The bending moment can be plotted as beam diagrams in the Y and Z direction. Then there is also maximum and minimum values for stress under tension and compression. It looks like the highest stress is near the upper portion of the frame, and it doesn't seem to be a concern. However, displacement may be a concern with the welding process. And it is important that we consider the motion of the robot arm. Let's begin by copying the current study and change it to a normal modes type. Here we are looking for the natural frequencies of the weldment without the applied load. This again meshes and solves very quickly. Taking a look at the result plots, we will start by looking at the first mode shape at about 43 Hz. Animations also aid in observing the behavior of the model. We can see that the least amount of stiffness is in the Y direction. Let's take a look at the next mode shape. It looks like this one resonates at almost the same frequency, and it is a bigger concern due to the motion of the robot arm. Let's take this a step further using a dynamic load. Once again, we will make a copy of the previous beam element study and change it to direct transient response. Now when we edit the load, there is an option to add a timetable, or define the dynamic behavior of the load. We will apply the 2000 Newton load over a fraction of a second and let the robot rest. There are additional settings for the amount of data we want to collect over time. In this case, we will take the results over 100 time steps, which is adequate. The more the better, keeping in mind solve times and file size. Also, we don't want to forget damping. There are options for structural, Rayleigh, and modal damping methods. Now we have the ability to see the results over time instead of a steady state. We can see in the graph the frame oscillates at a nominal distance after the robot moves. We may be able to save money on material costs by going with a smaller tube size. Since we are in the CAD environment, we can make the change to the 3D model, or in this case we can simply change the cross-sectional properties for the beam element. After running the solver, we can see the deflection has slightly increased and oscillates more, but our design requirements are still satisfied. As you have seen in this demonstration, Autodesk takes us beyond linear static studies and utilization of shell and beam elements to gain a full understanding of our design. Run quick what-if scenarios to ensure the structure is sound but not overbuilt. Welcome to this demonstration for testing the strength of the components in this differential. Will the bodies yield under a large load condition? Do we have enough bolts, or should we optimize the design and use fewer? Should we consider changing the size of the bolts? Taking a look at our first plot, we can see there is stress on the middle of the hub. The probe tool will help us to find out if it is going to be a concern. With the stress at 79 megapascals, we know it is not going to be an issue. What about the bolts? Let's begin by taking a look at the axial force that is causing tension or compression on each bolt. The largest amount of tension is 67 newtons. What about shear? The load on the gear is certainly going to impact the possibility of shear on the fasteners. Using these plots, we can check both directions and calculate the total shear for the worst case, which is nearest to the load on the gear. Once again, by using the probe tool, we can check the results anywhere on the model or on any of the 12 bolts. A simple spreadsheet calculation will help us to validate our design for the fasteners. By entering in the axial and shear forces, we can compare it to the allowable values for a specific bolt size and material type. It looks like we will have no problem with this configuration. The factor of safety is well beyond our requirements. Remember, this is a mass-produced assembly. We can save money by reducing the number of fasteners. Let's make the change, and also take a minute to see how this study is set up. First, we will reduce the number of bolts from 12 down to 8. Then the setup for the analysis is simple. We will constrain the center of the hub, which prevents it from moving. Then apply a total force to the teeth on the gear of 5,000 newtons. Next, we have the bolt connectors. There are two options when analyzing designs that have fasteners. First, the 3D models can be left in the study and they will be meshed as solid elements like the hub and the gear. This option involves a lot of work setting up proper contact conditions as well as lengthy solve times. The second option is the use of connectors. They take less time to set up and solve several times faster than solid bodies. As you saw earlier in the video, they also provide results like axial and shear forces on the bolt, and that is exactly what we need to know. Notice the results take into account the material and preload, providing the information we need to make informed design decisions. Now let's generate the mesh and run the solver. Just like the previous design, we will begin with the axial force on the bolts. It looks like the worst case is slightly higher than the 12-bolt design at 73 newtons. Nothing to be concerned with there. How about shear? In direction 1, we have 322 newtons. And in direction 2, we have 1,588 newtons. Now is the moment of truth. Will the 8 bolts be sufficient for this design? The results show the 8-bolt configuration is going to be enough. What about the size? Let's try 6 millimeters. We may even be able to save on size as well with a factor of safety above 5. As you have seen, we are able to run quick what-if scenarios to find the best design possible for the differential, all before a single prototype is built and tested.
Who is M2 Technologies? M2 Technologies is the leading manufacturing design solutions provider in the Northeast, providing services such as training, consulting, and project shadowing. We are a simulation specialized Autodesk Gold partner, as well as an Autodesk authorized training center. We have a deep roster of talented technical specialists with expertise in design, data management, CAM, and simulation tools. We have several locations throughout the Northeast, but we provide services all across the USA. Thank you for your time today.